Welcome to Manifested Publishers.
Welcome learners, my name is Stephen Kariungi, and today we continue with our topic of discussion, and the topic is reaction rates and reversible reactions. So far we have discussed 5 factors that affect the rate of reaction, that is concentration, temperature, surface area, catalyst, and light. There's only one more factor that is remaining, and this is pressure. And it happens that pressure affects the rate of reaction, and especially where the reactants are gases. And the reason why the pressure affects the rate of reaction of gases is because gases are compressible. So when gases are compressed at a very high pressure, then we have more effective collisions between the gas particles, and for that reason, the rate of reaction increases. So we are saying that pressure affects the rates or the rate of reaction of gases, but not liquids and solids. And the reason why that is the case is that this is because gases are compressible. They are compressible, or they can be compressed. And as a result of that, when gases, or when the pressure is increased, the gas particles collide more, leading to a faster rate of reaction. So when the gas particles are compressed at a very high pressure, then those particles will collide more, leading to a faster reaction, and vice versa. That when the pressure is lowered, the gas particles will have less collisions between them, and therefore the rate of reaction will be less. So as far as the pressure is concerned, we will not discuss that in a lot of details, because we are going to come across pressure again when we discuss reversible reactions. So at this stage, we are through with the reaction rates, and now we go to reversible reactions. And of course, as the term suggests, reversible reactions, those are reactions that can be reversed. And what means that once the reactants have been changed into products, we can get the products and change them back into the reactants. So we are saying that these are reactions where reactants are converted into products, and then the products converted back into reactants. So in other words, we are saying that the reaction is reversible. We'll have an example, or we'll have some examples. One is that if you have ammonium chloride in solid form, and then the ammonium chloride is warmed, then you warm it, you'll find that this ammonium chloride will change into ammonia gas plus hydrogen chloride gas. That is on warming or when you heat. On the other hand, if you allow the two gases to cool, they will change back to ammonium chloride. So this is an example of a reversible reaction. So we are saying that when ammonium chloride is warmed, it changes into ammonia, which is here, and hydrogen chloride. Gas, those two, and which when cooled change back to ammonium chloride. So that's one example of a reversible reaction. We'll take more examples. We have copper 2 sulfate crystals. And copper 2 sulfate crystals, these are blue crystals. But when they are heated, when you heat those crystals, they change to copper 2 sulfate anhydrous, now without the water of crystallization, and the water is lost, and the color changes to white. So we get a white powder. We get a white powder. So that is as a result of losing the water of crystallization. If that water of crystallization is added back to the copper 2 sulfate, then we go back to what we had earlier on cooling. We go back to copper 2 sulfate that is hydrated with 5 molecules of water of crystallization. So this one just adds back to this to go back to this. When you heat, this one decomposes to give those two. Another example is if you have cobalt 2 chloride, also in crystals. These are pink crystals, and when you heat, you get cobalt 2 chloride plus 6 H2O. That is, the 6 molecules of water are lost, and the color changes to blue. The color changes to blue. So if you put the states, that's a solid, is a liquid, a solid, a liquid at room temperature. So if you reverse that on cooling, we go back to the pink crystals of hydrated cobalt chloride. We can still take another example of when we have iron plus water. When iron reacts with water, this is in form of steam, we get triion tetraoxide, which is an iron oxide, plus hydrogen gas. So if you balance the oxygen with this 4, and then this will be 2, and if you cool it, So again, the reverse occurs. So that's another example of a reversible reaction. So basically, we have seen a number of reactions that can be reversed. And the assumption here is that the products should not be let to escape. If, for example, it's a gas, this is a reaction that needs to be done in a closed vessel. A closed vessel. So this is a reaction that is reversible. Same case applies to all the other reactions that we have seen. So basically, we are saying that these are examples of reversible reactions, reactions that can proceed in both directions. Reactants can be converted into products, and products can be reverted back to reactants. So the first question, what are reversible reactions? Number 2, explain why when solid ammonium chloride is heated, it disappears. Of course, it doesn't leave any residue. And number 3, write 3 equations to demonstrate reversible reactions. So we'll stop there until the next lesson. Goodbye.